Hello everybody. Thank you all for being here. We will present fast complexity, a fabrication method for the construction of lean concrete slabs using two different additive manufacturing processes, binder jetted formworks and 3D concrete extrusion printing.
Our research project is a collaboration between digital building technologies and physical chemistry of building materials at ETH Zurich. We are Anna and Andrei, and we are representing our co-authors, Dr. Lex Reiter and Professor Benjamin Dillenburger. We will start with a short background to explain the reason we are interested in concrete slabs. Load-bearing slabs represent up to 85% of the weight and cost of a multi-story concrete structure. Most slabs nowadays are monolithic and with planar soffits. The simple shape is dictated by the cost of formwork, which considerably exceeds the cost of concrete. Nevertheless, the visionary work of engineers and architects like Pierluigi Nevi, Felix Candela, and Hans-Dieter Hecker highlighted the important benefits that stem from articulated slabs, which are more performance structural systems relying on optimized geometry for improved stiffness. However, materially optimized slabs usually require bespoke formwork solutions that come at a high cost due to the one-time use. As such, they are often a premium product for structures for which slab weight is of critical importance. The available choice of mass-produced formwork systems for ribbed or waffle slabs is limited. For uniformly distributed orthogonal grids, the waffle slabs, for example, use modular plastic shells to create structural voids and integrate services through transversal openings within the structural ribs. Digital fabrication has been used recently to enhance the potential of ribbed slabs, initially in prototypes and then in build projects. Complex geometries can optimize the use of material, integrate precise reinforcement alignment and building services, as well as showcase an expressive aesthetic of concrete. However, these non-planar geometries are fabricated using complex formwork solutions involving multiple digital fabrication processes and manual concreting. For example, for the Smart Slab, the soffit was defined by the 3D printed binder jetted formwork, the upstand ribs by laser cut plywood sheets, the service voids by FDM 3D printed formwork, and moreover, two different concreting processes with distinct mixes were used, casting and spraying, and finally, 3 types of reinforcement were used: fibers, rigid bars, and post-tensioning. All these different processes have their own supply chains that are difficult to manage and are liabilities for contractors. In this regard, the automation of the concrete process can make complex slabs more feasible.
There are excellent examples in the state of the art exploring novel fabrication methods for concrete slabs. To give a few examples, we have the shotcrete ribbed slab from TU Braunschweig, the lightweight concrete ceiling from TU Graz, and the topologically optimized bridge from TU Ghent. By directly applying concrete in a digital process, we can simplify the construction with a significant margin and reduce the number of different fabrication processes involved. Nevertheless, the resolution of concrete printing creates a distinct, coarse, layered texture and has limited geometric freedom. Our research proposes a third approach, in which only two processes are used for the fabrication of slabs: binder jet 3D printing for the soffit formwork and concrete 3D printing. This approach takes advantage of the 3D printed formworks to produce high-resolution visible surfaces, but only uses a single concreting process. The 3D printing process developed at ETH Zurich is based on a set-on-demand process that uses a Portland cement base mix and a calcium aluminate cement paste accelerator. By controlling the amount of accelerator dosed during processing, we can change the viscosity of our filament to create a continuous transition from digital casting to concrete extrusion printing. We tested our approach in a series of 3 prototypes. The first one used a single piece of formwork. Here, the concrete has a similar hardening rate for the soffit as well as for the ribs, and the print path was created as a generic pattern formed by parallel lines that cover the entire surface. The second one used 3 pieces of formwork treated with 3 different release agents to test removability. Furthermore, the accelerator was dosed in 2 different concentrations to get a very fluid concrete for the soffit and a more stiff filament for the ribs. For this prototype, the print path was adjusted to follow the patterned ribs of the formwork. As you can see in the right image, not all of the release agents performed well. We decided for the middle one, which was a commercially available water-based release agent. Fast complexity is suitable for fabricating large slabs in discrete segments. The formwork for the soffit can be used for the repetitive parts of the slab, but it can also be customized for edge and corner conditions. The concrete extrusion process can subsequently adapt to these conditions, and it gives the flexibility of customizing the upper structure. For instance, the upstand ribs can be differentiated in width and height to stiffen the slab locally or to respond to the loads and support conditions. Also, the voids for building services can be customized and integrated seamlessly in the concreting process without the need for formworks. In our prototypes, we consider the fabrication of the slab in discrete nodes with area of around 1 square meter, centered on the intersection of 2 ribs. The height of the slab can be adapted by the concrete printing process and depends on the span of the slab. The interstitial field is a thin shell with a thickness of only 2 to 3 centimeters that integrates a carbon fiber mesh reinforcement for stiffness and for mitigating shrinkage cracks. The nodes are reassembled through bidirectional post-tensioning, first in beam-like elements that span the width of the slab. Then these beams are post-tensioned on-site to form the two-way slab. The amount of accelerator in the concrete mix is dynamically controlled. The first 2 layers include a minimum amount that allow the concrete to perfectly fill all the articulations of the 3D printed formwork. Once an initial layer of concrete has been uniformly distributed across the entire surface of the formwork, the concrete extrusion process is paused and the post-tensioning tubes are positioned. Further tubes can be integrated at different positions without the need of additional markers. The carbon fiber reinforcement mesh is placed after the second concrete layer. Subsequently, the upstand structure is 3D printed in concrete, integrating bespoke service openings. The resulting surface quality of the soffit is a function of the viscosity of the concrete mix and the trajectory of the print path. As earlier mentioned, for the first prototype, the tool path was independent from the geometry. In the second prototype, shown in the middle image, the tool path followed only the major ribs, leaving the smaller ribs with imperfections. For the final demonstrator, the initial layer of the tool path followed the entire geometry of the soffit, resulting in the best surface quality.
The final prototype included 2 1 square meter slab modules that were made using the same 3D printed formwork. The 2 parts were assembled using a single post-tensioning tendon, and the upstand ribs were monolithically connected with a concrete mortar cast in place. The interface between concrete parts can have a perfect alignment of the articulations due to the precision of 3D printing. Moreover, seams between formwork parts can be integrated in shadow gaps, and metal trims can also be integrated. After the experimental work, we can conclude that the accuracy of the formwork allows for more complex interfaces between the segments of the slab, therefore making it possible for more intricate and performative interfaces between concrete components. Even if 3D concrete printing is fast, it cannot compete with the fabrication speed and structural performance of cast concrete. In a potential future implementation, only the outer contour of the ribs can be 3D printed and the resulting light shell transported to site. The reinforcement baskets are added on site and the ribs are cast in situ. This allows the continuity of the structural system and produces smarter and lighter parts. We can conclude that the potential of our system lies in the possibility to fully customize the formwork, but also in creating small series of elements that reuse the same formwork. Finally, we would like to acknowledge the contribution of our colleagues, partners, and collaborators. We thank you for your attention, and we are happy to answer some questions.